Hello friend, welcome to this new video. In this video we will see the concept another structure of algebra, that is vector spaces. So first structure of algebra is a group, second structure was a ring, and third structure is a vector spaces. In the group there is a one non-empty set, and on the set one binary operation is defined. In the vector space, in the ring there is a one non-empty set, and two binary operations are defined with eight properties. In the vector spaces there are two sets. One is a abelian group and second is a field. So important point to note here that here V is an abelian group as a one structure and field is another structure. What happens in the vector spaces, we combine these two, and if we if these two structures satisfies four properties, it is called as a group. So if let us consider V as an abelian group, and let us denote a binary operation on that group is a plus. It is not that plus usual addition as we know. It is just a notation symbol used to denote a binary operation on a group, on an abelian group V. And F is a field. Field means it is a ring with commutative ring with unit element, so it has a two binary operation, one is plus and other is a dot. Now here we define a function from F cross to V. That means here we are combining two sets V and F and getting a product in a set V, such that for alpha belongs to F and V belongs to V. V belongs to F means one element from F, one element from V, and we are taking their composition alpha V belongs to V. Then V is called as a vector space over F with following properties. First properties, let us consider alpha plus beta and V. So binary operation between alpha plus beta and V, then it is equal to alpha V plus beta V. Second property, alpha and two vectors u plus V, then we get product alpha V plus alpha u. Third one is alpha beta into V, denoted by third condition, so alpha times beta V. And fourth one, alpha V, 1V equal to V. So here the alpha, beta and 1, these are the members of F and they are called as scalars, and U, V, these are members of V and they are called as vectors. So members of V are called vector, members of F are called scalars, and to denote their combination in a single symbol, we write it as a V of F, that is vector space over the field F. Now let us see the examples. Suppose F is any field and V is a set of ordered pair, alpha beta are members of F. So all order pair, set of all order pair, and we define the addition and scalar multiplication as alpha 1 alpha 2 comma plus beta 1 comma beta 2, order wise addition alpha 1 plus beta 1 comma alpha 2 plus beta 2, and alpha times alpha 1 comma alpha 2 equal to here you can see this definition, alpha times alpha 1 comma alpha 2 equal to alpha 1 comma alpha 2. So with these two operation, first one is addition and second is a scalar multiplication. So both are elements of in the first again we get order pair alpha 1 plus beta 1 comma alpha 2 plus beta 2. So again it is member of V. And in the second scalar multiplication, again we have order pair of the type alpha comma beta, so again it is a member of V. So obviously first property, that is closure property, is satisfied. Now consider 3 alpha 1 comma alpha 2 beta 1 comma beta 2 gamma 1 comma gamma 2 members of V. Then we see that this associative property is satisfied. Again, let us see this. If we take a 0 comma 0 order pair and add this order pair, so we get gamma 1 plus 0 comma gamma 2 plus 0. So gamma 1 scalar, 0 is a 0 element of F. So therefore gamma 1 plus 0 means gamma 1, gamma 2 plus 0 means gamma 2. So again we get a order pair member of V. And 0 comma 0 plus gamma 1 comma gamma 2 equal to gamma 1 comma gamma 2. So these are both belongs to V, and 0 comma 0 played a role of additive identity in the structure of V. And here an important, see this minus gamma 1 comma minus gamma 2. If we add this to gamma 1 comma gamma 2, we get 0 comma 0. Therefore this minus gamma 1 comma minus gamma 2 played a role of additive inverse. So all the properties, that is closure, associative, existence of identity, existence of inverse, both are satisfied. Therefore V is an abelian group. Now let us see the properties of the vector spaces. See these conditions. First, if we take alpha comma alpha plus beta into elements of V, elements of V is denoted by alpha 1 comma alpha 2, then we can see that it is again an order pair and member of V. So first property of vector space is satisfied. Now see the second property, alpha times two members of V, alpha 1 comma alpha 2, beta 1 comma beta 2. Then we have added the internal 2, these two we have added, and we get alpha times alpha 1 plus beta 1, alpha 2 plus beta 2. Now by definition of scalar multiplication, we can multiply these two by alpha and we get this one. Now separating this alpha and betas, we get alpha times alpha 1 comma alpha 2, beta alpha times beta 1 comma beta 2. So second property of vector space is satisfied. Now see the third property. Here we have taken this product alpha comma beta and multiplying to this element of vector space beta 1 comma beta 2. Now multiply, this is considered as a single vector, so that is like alpha in the definition. So alpha beta into beta 1, alpha beta into beta 2, and separating this we get alpha times beta in bracket beta 1 comma beta 2, and this is a fourth one as usual. So all the property of vector spaces are satisfied. Therefore V is an vector space. This is one of the important example. Now again consider example of set of all m by n matrices of real numbers or complex number, and we can see that all the properties of vector spaces are satisfied. We know how to add the vector matrices. Addition is a component wise, and in the short we have used this notation to denote a matrix Aij. So consider three matrices Aij, Bij, Cij, all belongs to M, and consider any two elements alpha beta belongs to R. Then here addition is component wise, as we know this addition we have defined component wise, and scalar multiplication is again component wise. Then we can see that the matrices are satisfies the closure property. This one is associative abelian property. This one is associative property, and 0 comma 0, if all the entries are 0, it is called as a zero matrix. And if I add this zero matrix, we get zero matrix is an identity element of this set. Now let us see here minus aij. If we might take minus aij, all the elements are negative of aij of that matrix, then we get a zero matrix here. This is a zero matrix, that is identity. Therefore minus aij an additive inverse. So this shows that M satisfies the properties of abelian group. Again, see the vector space properties. Alpha is a scalar, aij and bij are the matrices. Again, add matrices first and then multiply by scalar, and then multiplication by scalar gives this term, and we can separate this one is like this. So first property, this one is a second property, alpha plus beta is a scalar. Multiply this alpha plus beta by aij, we get new matrix, and again separating the scalar. Third one is alpha times beta aij. Beta aij, first multiply by beta and then multiply by alpha. So we get alpha beta multiplication and aij. So we can take common alpha beta as a aij. So all the properties of vector spaces are satisfied. I hope you have enjoyed it, and thank you for watching.